Stars are amazing. Stars have been capturing the human imagination since, well, forever. Ancient Egyptians worshipped our nearest star, the sun. Ancient Greeks connected the dots between the stars in order to paint pictures of their gods. We even made nursery rhymes about them in the 1800s. Even today, we spend billions of dollars and even risk human lives to take better pictures and get a better view of what they look like and how they live. So in this video, we're going to walk through the life cycle of a star. How does it form all the way to how they eventually die? So, stellar evolution, or you can call it the life cycle of the stars, or you can call it how we are all made of stardust. We'll get to that by the end. This is our galaxy, the Milky Way, and we live right about there. So, we are going to break up this lecture into size. So, we're going to start with stars that are average size, like our sun, and see what their life cycle is going to be like. So here we have a little recap of what we did in the first part of the unit, which is we looked at spectra, and we looked at how scientists use spectra to determine what stars are made out of. So this star down here is made up of iron and magnesium, and if you layer these on top of each other, you will get this spectra. Now, while stars are beautiful and they come in all different colors and all different sizes, it's more than just that. The color and the size of the star tells us a lot about the star. Now, our star is this yellow orangish one right here. It's a G-type star. You see that there are some that are smaller and redder and some that are bigger and bluer. So as we talk about average size star, and all stars actually, they start to form in a nebula. And the nebula is that cloud of gas that ends up making up the star and it can be light years across, and the different colors mean that there's different gases. So like this one has lots of pink, and that's from the hydrogen. So another way of explaining a nebula is to call it a stellar nursery. And it starts to form a star when that cloud of gas starts to collapse on itself due to gravity. And so here goes the Orion Nebula. Then we have the Horsehead Nebula. Some of these are just pretty, like the Eagle Nebula. And if we look closer at the end of the Eagle Nebula over here, we'll see that we see the first beginnings of some brand new stars. Now, after that cloud of dust starts to condense a little bit more, we'll switch from calling it a nebula to a protostar. So this is the earliest stage in star formation. But fusion hasn't happened yet, so it's not quite a star, because that's that threshold. If it has fusion, it's a star. If it doesn't have fusion, it's not a star. So we have, as more mass accumulates, so one dust particle hits another, hits another, hits another, and it just starts to snowball. And as all that mass accumulates, gravity goes up, and as gravity increases, it starts to attract more material, which makes the gravity go up, which makes the mass go up, which makes gravity go up, and eventually all this gravity and mass, and then gravity starts to push the mass together, and the temperature starts to go up, and pressure starts to go up until oh, wait, not yet. So you have the protostar here. We have jets coming out the sides of them as they get hotter and hotter until 15 million degrees Celsius. And at 15 million degrees Celsius, fusion begins. Literally, you're taking two atoms or 4 atoms, depending upon how it's happening, and shoving them together to make new elements. So this is how new elements are actually made in nature. They get fused together inside stars. And the stage is called the main sequence star. So this is right in the middle of the star's life cycle, and it's the most stable part of a star's life. You're taking stars take hydrogen and they shove them together to make helium. Now, as you can see over here in this little drawing, there is not enough subatomic particles here to account for all the hydrogen that go into making this helium. There's a few free neutrons that go away, that fly out, but where does that extra mass go? So when your teacher in middle school taught you about conservation of mass and conservation of energy, they probably said something like matter cannot be created or destroyed, and energy cannot be created or destroyed. But it's not quite right. So this is what Einstein is famous for. Einstein is famous for an equation E equals mc squared. So what it means is if you destroy a little bit of matter, you make a ton of energy. And if you destroy a ton of energy, you create a little bit of mass. And so here you can see that there's just tiny little bit of matter destroyed, but it creates massive amounts of energy in the form of heat and light. So, if you have a main sequence star that has so much mass, why doesn't it just collapse under its own gravity and just shrink into nothing? Well, fusion. So they counteract each other. So gravity forces is pushing the star in on itself, and fusion is causing outward pressure, holding up the star against the force of gravity. And this back and forth, this balance that's eventually reached, that's what keeps a main sequence star so steady for so long, because those two things, fusion and gravity, are balanced out. And here goes another diagram showing that. And this offers the most stability in a star's life. And so this is going to be the longest part of a star's life. Like our sun is going to be a main sequence star for 10 billion years. And then it's going to change. But it's only been like this for about 4.6 billion years. So it still has over 5 billion years to stay steady as a main sequence star until it turns into a red giant. So this is our sun, and this is what it will become at the end of that 10 billion years. So after 10 billion years, it runs out of hydrogen. And when it runs out of hydrogen, the core collapses, it heats up to 100 million degrees, and then it starts fusing helium together to make carbon. So all that helium that came from that is over those 10 billion years of hydrogen fusion is now coming together to make carbon. Now, when this happens, the outer layers on the outside of the core get pushed out. They expand out because helium fusion is so much hotter, so much energy, that it actually pushes those outer layers out. And as those outer layers get spread out, they cool off and they become red. Because remember that with stars, red is cool, blue is hot. Here goes some size perspective. So you have Earth, the sun, and a red giant. Called giant for a reason. So the star will eventually run out of helium for fusion, and then the star will blow off the outer layers in these pretty clouds that last for a relatively short time, like thousands of years, called planetary nebula. So here goes some pictures of some planetary nebula. And then after the planetary nebula kind of goes away, and you're left with just the core. And the core of the sun-sized stars ends up being a white dwarf. It ends up being all that carbon left over from fusion during the red giant phase, and all that carbon is super condensed and super hot, and it's called a white dwarf. It is basically a really, really hot diamond, hotter than the surface of the sun because it's pure carbon. And it's dense. If you took 1 teaspoon of it, it would weigh a ton. And here goes a picture of a binary system with a white dwarf here, and a main sequence star here. This is Sirius A and B. And then this is what scientists think happens next, that the white dwarf eventually cools down to become a black dwarf. But it takes so many billions of years for them to cool down that our 14 billion year old galaxy, or no, sorry, 14 billion year old universe hasn't been around long enough to actually produce any black dwarfs. It's going to take a few more billion years to actually have any of these around. So now that we know what the life cycle of a normal average size star is, let's go and in the next video look at what happens with big stars.